convolutional coding, which is a part of channel coding. The channel coding we had already started. So this is an optional block that we know because it's the shaded part. And let us quickly go to the convolutional. That is convolutional coding. Channel coding, we understand that we have a k length input and finally which is n greater than k and n length output, and this and the because that we know that is we put some parity bits. Sometimes we put a rectangular parity. Rectangular parity gives you not only the error detection, also error correction capability that we have studied, and we have calculated certain the probability of the undetected error and all these things. And the convolutional code, it's a type of channel coding technique. That is convolutional code means you have the k input, finally it will come to n number of output, n is greater than k, but that it is characterized by both n, k, and there is another parameter that is capital K, which is called constant length. Okay, this is called constant length. That we are going to discuss. Now the convolutional encoding, just if I see that this is my information source, that is M1, M2, Mi, and finally after this, this code word sequence here this is called code word, and this is called message word. That's why it is M. Okay. Now this U is G of M actually. That means here it is all U1, U2, UI. Okay, and this UI means this UI is basically U1I to UJ, UNI kind of thing. That means each U is dependent on some sort of a in different values of this small u. So let us see. It is representation by it is little clumsy, but if we do it, it will be clear. Say this is the shift register. Okay. Now this is the k into capital K shift register. That is 1, 2, 3 k into capital K. Capital K is the constant. Now that means you are sending the message bit that is going to the input to the shift register M1, M2, MI, and all these things. And what it is doing, that means say each, and there are certain adders, and you see there are k into k number of shift register, and I have n number of say a modulo 2 adders. That means XOR block. This is XOR. Now what it does, that means see it is giving the input. It has certain initial state, maybe all 0 or whatever it is. Initial state is given, and you are slowly putting, say, when all the things are populated, or even first bit has come here. So that means, say, it is. Please remember, it is coming in this way. Okay. So M1, say all other states are all G. Okay. And what it does, that means it does, say, this adder, this not adder, this is a modulo 2 adder, that is XOR block. It has certain connections. That means it is taking M1 XOR 0 XOR this key. Similarly, 2, it has this XOR, and this XOR. Okay. Not that it is exhaustively connected. It is not fully connected. Similarly, this one, it is connected only with this and this. And finally, you have, so that means after doing the XOR, it has certain values over here. It has certain values over here in the same in block. So, and if I just switch it, then what I will get? That means this, as there are n number of things, U1I to UNI. That means U1I, U2I. This is U1I, U2I, U3, UNI kind of thing. Okay, for ith one. That means you have MI. If it is MI, so ith one has gone. Okay, so say here it is M1, this is M2, that is MI. Say here it is MI minus 1. Okay, like that. Okay. U in I. This is that. Okay, and then this is the code word sequence that U I line vector means all this n line vector. Okay, so that means here that so this is my convolutional encoder kind of thing. Let us take a simple convolutional. So this will be, say I have an input bit. I have an input bit. I have two adder. Earlier you see that in the previous case that adders were there are n number of adders. N number. So what they have done? Say they are equal to 2. Say that is one adder this side, one adder that side. They have for representation purpose. Okay. So what that means? First adder, or say this is first adder. This is second adder. Now first, so constraint length is 3 k into k. This three blocks are present. You see three length shift register. That 3 length kk stage shift register, 3 length shift register, and 2 number of modular adders. Okay. Then this is 3 length shift register. That means when if it is there are 3, say that is a M1, then M2, then M3. So in this way things will move. Okay, say at a point, say it is like that M1, M2, M3. It is like so it will come and it will come from this side. So when I have like this, then I will first one will do the XOR of all 3 and will give U1, and next one will give the XOR of all 2 and give this one. Say that means if the say if it is for now, if I just clean it, that means say if that for if you remember, that means for ith one, okay, say I have U1i to UNI, so here it is for ith one, this is U1i, U2i for say ith bit. Okay, so that means this is my that U1i is the first port symbol and U2i is the second port symbol. So for each MI, you see that is for each MI 1 bit it is input, there are 2 bits output. Okay, so rate is 1 by 2 and constraint length is 3. So that is 3 length. So convolutional encoder, you see that in each input bit there are 2 output bit. Okay, and these 2 output bit they are basically they are dependent on the input. Say it has come here. Okay. Now it is dependent on this current bit, previous 2 values, previous 2 inputs are here, and then you are doing the XOR. So that means mi minus 1, mi minus 2. That means the constraint length is 3, that is 3 length shift register, and the current output U1i is dependent on mi minus 1 and mi minus 2, and U2i is dependent on mi and mi minus 2. Okay, so the convolutional encoder, that it is represented by the rate is half and k equal to 3, and usually the connection diagram is also you need to specify. That means whether first one is 3 connected or second one is 2 connected or which 2 it is connected. So these things also should be informed. Okay, this is called, yes. Capital. Okay. Actually, this it doesn't matter basically. That it is just a you see the white. That's why I told that this one is little you know little the representation wise little clumsy actually. You need not write like this. I mean, from the book's perspective, they can do something like generally people do 1, 2, 3 capital K stage register. That's it. Okay. are generally we assume that one bit will be shifted. What they have done, shifted in k at a time and all these things they have done in this way. But generally what do we do? It is some 1, small k equal to 1, that k. So 1 bit, because normally shifting is 1 bit shift now. But they have made it generalized kind of thing. At one go, there's a small k bit shift, and they have some k into k number of. In that way, they have represented. The first representation was little comes. So first you make the life simple. 1 bit at a time shift. Small k equal to 1, which is k capital K. Okay. Now you change it, so it is 2 bit shift kind of thing. Okay, that means it is mi and mi minus 1 both will come. Then again mi plus 1 and mi plus 2 will come. So in that case, your shift register, that means that will be equal to 2 into k type of shift register, means even number of shift register kind, because 2 bits will enter and 2 bits will go out. If it is 3 bits entry, then it is 3 bits out kind of. So they have made the first representation should not have been like this actually. Anyway, so generally we do 1 bit entry and 1 bit exit kind of. Is it okay now? Then because I am physically explaining 1 bit entry, 1 bit exit system. Okay. But anyway, so even if you do some kind of a 2 bit entry system with 3 length, you cannot do like that. Okay. In that case, then you have to put a 4 kind of thing, 2 bit entry from here, 2 bit going out. So 4 they represent it in 2 into k kind of thing. But k is a constant. Anyway, so in this case, that they do something like this. Say that means your message is 1 0. Okay, this is your convolutional encoder. Encoder means like this. Please try to understand. Encoder is this. This is your encoder. Okay. So now first this it is which side it is moving. Anyway, it is both. Anyway, so it is moving in 1 0 1. The first one, say I am assuming that it has reversed it. So it has first moved 1. Initially the encoder was at null state. That means initially the encoder was all 0, and it has come like this. Now what will be your U1 and U2? U1 will be, that means 1 0 1 1 0 1. So U1 is 1. U2 is 1 0 1. So that means at the first instant you have that entry is 1, and you have got your code word was 1. Then your entry is 0. That means that's why that 0 has come. So it has shifted 0 1 0. So that means this one is, it will be 0 0 is 0, and 0 1 is 1 1 0 is 1. So you have 2 code word. Means 1 1 0. This is another channel word or code word kind of thing. So similarly, then when the shift register is completely populated 1 0 1, then you will have a 0 0 kind of thing. And finally, you have to do a complete flush kind of thing. That means complete flush kind of thing means this. You have to go another two clocking cycles. So that means 0 1 0. 0 1, you have this, and next clock means all 0. Then you have all 0, so you have got all 0. So what is your output sequence? Output sequence is your 1 1 1 0 0 0 1 0 1. So 1 1 1 0 0 0 1 0. So when you have some sort of a 1 0 1 is the input, so this is your output. This is your basic sequence. This is your channel sequence. Okay. So and in this case, because see last 0 0 we don't consider. Okay, because that is the relaxed case actually. Okay. So now this is called the rate half, and k equal to 3. That means 3 means this length 3, and each one bit, each one message you are getting U1 and U2. Okay, that's why that rate is half. Please remember, if this is 3, this is not 6. Please see, the length of message bit is 3, but length of the control bit is not 6. Please try to understand why it is not that, because last phases you have 2 more things are there in order to flash. See, these 2 1 you have to flash, that's why you have got an extra 4 bits. So don't think that M length is 3, so U length should be 6. No, it is the rate means here each input you are getting 2 output. That is the rate. Okay. So that's why they put it some sort of a effective code rate. They just say effective code rate. Effective code rate means yes, I am putting a 3-bit input and finally I am getting a 10-bit output. So this is called effective code rate, is 3 by 10 kind of. Okay. That final bit into the encoder needs to be shifted through the encoder and all output needed to be decoding. Anyway, so there are certain polynomial representation. Okay, because finally, see at the decoder side, so what the decoder is doing? Decoder is getting, this is the decoder means at the receiver side, you will get this U1, U2, U3, U4, U5, U6, U7, U8, U9, U10. From there, you have to get M1, M2, M3. Okay. For that, you need to have this connection information and this connection information. Also K and the code rate half, this information. Okay. So now for this connection information, we generally represent by polynomial kind of thing, generator information. That generator for the first one is that 1 plus x square, that is all 3 were connected. It is 1 plus x square, and this one was, the next one was that 1 plus x square line. In this way we represent, and finally they do this calculation. So if you in that way, if you do the connection, that you will see that what is your mx, because if you do this calculation, m was 101, so that means this is your g1x, this is your g2x. Okay, and m was 1 plus 0x plus x square, 1 plus x square. Okay, and if they do these things, if you just multiply and play a little bit with it, then you will find that mx g1x, mx g2x, and finally they put this 1 plus x, finally 0x square, and finally this one, and finally what they will get, what is this ux, from there this from these coefficients, you will get the encoder out. So 1 1 1 0 1 1 1 0 0 0 1 0 1 1. Okay, so this is your U kind of. Okay, so in this way, people because if you do this thing, then actually calculating using the with the help of computer, it is easy to do. That's why people do this type of generating polynomial explanation, because by hand this is okay, but when your say k equal to something 5, this that's a big number, then it is difficult to do by hand. So when you are doing it in some programming language, then actually in this method people generally do. Okay, and there are certain state representation and state diagram. This you will find quite interesting, because the same thing, that means if you that because this is some sort of a that finite state machine kind of thing that most of you have already studied in digital electronics class. The same thing they have done. There is nothing. There are 4 states: 0 0 0 1 1 0 1 1, and finally depending on the input, how the overall machine will move to the state. That is the case. It is just a representation purpose. There is nothing great about it, and you know that they have represented that input bit 0 and input bit 1. That means that this is the representation actually. So you little bit see this picture. It will be, this is the output. This is all output kind of thing. That means it is getting the output and moving to the next state kind of. Okay. So that you study on your own, and if you see, that means you will find it that I was explaining, that register content initially it was relaxed. Then when the first bit is inputted, so that means what happened? Your register content 100, it was moving from this side. That is that 100. Now state at time ti. Okay. So this is 00 and 10. That means state at time ti and state at time ti plus 1. What do you mean by that? That means I can say this is one state, this is another state. Okay. Now that basically you see that they have represented in this way. Okay. Now just another. Okay, you see that 10. Same thing, you see that throughout you will find this 101101 there. And branch word at time ti. That means you see that it will be, but what was that? That U1 was all three is XORs, that is 1, and that branch 2 was 1 and 0 XOR, that is 1. In this way, they are representing the and this state ti plus 1, that they have kept 1. So in this way, they are also generating the output sequence, same output sequence kind of thing. It depends on this input. So that means it depends on this. That means each output, this output is dependent on this input, and this input is this one, and this states of the, that means states of the state is the register content. This input has moved here. Okay, see that first block is the same input. Okay, so now, so that means, and state is this one and this one. That means it depends on the state and the current input. Okay, state means the content of the registers. That's it. Okay, so you have this input, and finally you have this output. This is the convolutional encoding. Okay, now why the name convolutional? Because convolutional we have studied in linear system theory. There are certain idea of the convolution. Convolution is something like that summation hk x in minus yn in digital. Okay, so this is key. Okay, this is some sort of a this is the convolution. Now this on this one, you can get the idea of the why the name convolution. Just read little bit of that impulse response of the input. You please read that. See, suddenly impulse response. That H is the impulse response. So that means we explained why summation hk x n minus k. That hk was the impulse response. So they have also, they have for the encoder, they have certain impulse response. Now that what is the impulse response generally? If I in a normal case in a system, so what is the impulse response? Impulse response means I have a all zeros, suddenly I will put a delta t kind of thing, and what will be my output? This is my ht, and suddenly I have given a delta t. Or if I give a delta n, that means this is the delta n, what will be my say this is this is my agent. Okay, this is my. So similarly here also they are explaining that what is the impulse response of a sequence. That means the impulse response is 1 0 0. So it is a causal kind of thing, 1 0 0 and 1 0 0 and all 0 kind of thing. What is my output sequence? So this is that this is the impulse response. You see, this is the impulse response because this is the impulse like 1 0 0 kind of and now if I have a and what we know that what is my why impulse response is important. If I can break xn as a some function of delta n means delta n minus k, some sum of delayed impulses, then yn output also can be broken into sum of hn minus k. That we know from that's why the linear time invariance and all these things we studied. So similarly, that means if the input is something 101, that means which is some sort of a delay. I can say some sort of a delayed. So this is my impulse response 100. Then there's a means then this is some sort of a 1 into weighted by 1 into some 2 unit delayed impulse response. This delayed impulse. This is some 0 weight 1 unit delay impulse. So some sort of a for 1, what is input 1 means say I can say it is 100 kind of thing. So here we have seen that 111011. So sort of 1110. 0 means for our input 0, the output also it is all zeros. Now if it is 1, so if it is a delay, something like that. 1 means I can write it 1 0 0. Now 0 means I can write 0 0 0. Now this 1 means again I can write 1 0 0, something like that. Exactly I am doing the same thing. For 1 I am getting this is my output. For 0 I am getting this one. For 100 I am getting this one. So this is some sort of a crossing time. Okay. So what I have now for that 111011 I have a 2 unit time shifted 111011. Then I am adding it up. Then I am getting this is kind of output. You see that I have without doing this impulse response analysis, I have already got the same result. That means now we can say that convolutional encodes are linear. This is the basic definition. That means this is the basic idea. That means if I am just adding the input, my outputs are also getting added. Okay, with weighted adding time. Okay, so and there are different standard convolutional encoder. Okay, just this is some k-length 3 rate half. So you can do some sort of a you can read this quite simple. Convolutional encoding is quite simple. This is called a trellis diagram, encoder trellis kind of thing. That different code word branch, and there are certain popular convolutional encoder. Just like that, people don't use just any convolutional encoder. There are certain standard convolutional encoders that is quite used in the So there are certain that standard optimum, you see optimum short constraint length convolutional codes. That means you see the thing is that most of the codes are half. That means each bit you will, there are certain 1/3, half and 1/3, and there are certain constraint lengths. Okay, so 3, 7, 8, and the code vector is also given. Okay, so that means my point is that that people generally use the convolutional code from this length. Okay, what is predistance and all these things at this point. At this point, I am not going to cover this because this is generally those things, and those things need little more understanding. But that it depends on that is what type of convolutional code you are using. Basically, generally we check these characteristics. That means what is that probability of bit error and versus normalization. Depending on that, we decide that which one we should use. Okay, these are some certain from the handbook. They have given certain standard convolutional code, and so this one, and for the receiver side, how do we do this decoding? Okay, for decoding because at the receiver side you have to decode it. That this is the convolutional encoding. Now decoding generally we do with a beta decoder. Okay, now this is some sort of this is the formulation of the convolutional decoding. One is the maximum likelihood decoding. That means that probability of z given um, which is basically that over all u, whichever is the maximum probability of z, that I will get. This is called the maximum likelihood. Okay, so now that means that like that. That means say I am a binary communication kind of thing. I am sending S1T or S2T. I have a decision. That means if probability of Z, I have received something. Okay, now I will calculate probability of Z given S1. I will calculate probability of Z, the same probability of Z given S2. If probability of Z given S1 is more, then I will assume maximum likelihood principle says that most likely S1 has been found. As simple as that. Okay. So if probability of Z given S1 is greater than probability of Z given S2, I will decide that yes, it means that S1T has been found. That's why the probability of Z given S1 is high. Okay. Now the same principle we will use, and I am assuming some sort of that it is the Gaussian zero mean, and it's a memory-less channel, and finally it is a link dependent. So that means I have this product business. Okay, and with this actually we could as some standard algorithm, and we could calculate log likelihood and all these things, and finally we will get some sort of a theta decode. Please do this one. Electric channel is okay. Gaussian channel. This. Please try to write a simple code of this one. Sometimes the code is also available, but please try to understand that what is this beta convolutional decoding algorithm. Actually, this what they do. That means this is my input data sequence. Okay, I have my transmitted code word is this one. Okay, say I have my received code word is this. You see that I have an error over here. 300. And from there, that means I have received this one. I have received this one. I have some error, but I don't know where the error is. Say I know that this is some sort of erroneous things at the receiver. See, this is the actual thing in the transmitter. This is transmitted code word. That means this is a encoding, convolutional encoding. Now, after convolutional encoding through channel, you have sent this. You have received erroneous things. From here, you have to calculate some sort of an M prime. Okay, this part is called beta decoding. Is it clear? Now this Viterbi decoding, that is this one, because this is, as it is an algorithm, it is very difficult to explain it in a class actually. Because if you write a simple code, it's a 5 to 6 lines MATLAB code or Python code, I am telling you. Just if you write that, take a simple, say this, take something like this simple, this type of example, and if you solve it, you will understand actually. That it is basically a means maximum maximum likelihood principle actually. Okay. So and you will find out that, and generally in this way decoded trellis diagram people use it. It is just a basic commonsensical approach. They give certain means things, but actually it is quite simple. And depending on the path metric, what is the minimum path metric that you will choose, you will march to paths. This is quite simple, and this Viterbi decoder is computationally very friendly. Otherwise, it is very difficult that how will I suddenly decode these things actually. There are certain state metrics, and from there they try to calculate things actually. And I will request you, if you are rather maybe after the examination, if your time permits, that means try to do this decoder implementation. See, they have also this one. Okay, and it is, and otherwise that normal Viterbi decoder, that function is also available in MATLAB. I don't know, I'm not sure about Python, so you can also do that actually. Okay, so and we have a final exam on Monday, so just but be relaxed. It is, because as it is an online class, I understand that problem is there. So we'll try to take an exam on the means whole syllabus. Okay, so on Monday there is like that 45 minutes test kind of thing, and don't be panicked about grades and all these things. Everybody will get minimum B. That's it. That much. But at least attend the exam. That is important. Okay. Okay. Thank you very much. Yes. 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 Hmm. 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 FSK, please try to understand. FSK, PSK is in band pass zone. When you are talking about these gigahertz level things, when you are passing the signal through wireless and all these things, and these duo binary, I was talking in baseband. There are two different frequencies in two different chapters. Oh, thank you. I have seen your email, but from your email I didn't understand that. You explained so many things, but I didn't understand why the actual confusion. So, oh, thank you. So Monday is the exam.